Okay, hi everyone. Welcome to the meta learning workshop by Machine Learning at Berkeley. If you haven't already, please go to this link over here and download the repo for the demo part of the workshop. The dataset is also included there, so you don't have to download anything separately, and we'll be going over that together. Okay. So just as a brief agenda before we get started, first we'll start off by talking about what meta learning is, and then we'll go over a few different techniques on how you can do meta learning. So first, for what is meta learning, the motivation behind this area is that with many deep learning techniques right now, as you may know, oftentimes they require a lot of data, huge amounts of data. So the reason for this is because as your neural networks get much and much more deeper, there's a lot more parameters in them. So in order to actually not overfit to your training set and actually just model the data distribution instead of the specific examples in the training set, you need to have lots of training data. So this actually starkly contrasts with the way humans learn, because humans don't really need so much data to learn. And the reason is because we transfer knowledge between tasks. So if I show you something that you've never seen before, most likely you'll relate it back to something you've already seen and transfer that knowledge to be able to recognize the new object in the future. So our goal with meta learning is to understand how we can make ML techniques do the same sort of do the same as humans. So basically be able to transfer knowledge between tasks. So for example, let's say you've seen fruits before, but you've never seen any of these fruits in specific. So if I ask you which one of these images on the right matches the guava on the left, you wouldn't just treat this as a completely new object that you've never seen before. Instead, you might say, oh, all of these look like fruits, and some common properties of fruits is that the outside is one color, the inside is one color. So you would pay special attention to that and say, this probably looks the most similar. So our goal is to kind of take the knowledge that we know about other similar tasks and then apply it to a new classification task that has different classes that we haven't already seen before. So like another example is, let's say you've never seen this lizard before. Even though this might be your first time seeing it, if I show you another picture of it sometime later on, you'll probably recognize it again. So another example in practice that uses meta learning is meta imitation learning that's done by OpenAI. And basically what's going on here is that a person is giving a demonstration to a robot on how to pick up blocks and stack them up on top of each other. And initially the robot is just watching it, but later on it'll actually go through and perform the task on its own. So the way, when it performs the task, the environment is slightly different than when the person showed the task to it. And as you can see, the person is dropping the blocks a little bit more than the robot is. So it's understanding, based on previous knowledge, what parts of the demonstration are most important, and using that knowledge to complete its task on its own. Okay, so overall, the general goal with meta learning is that you start off with a lot of data and you put it through a meta learner. And this learner basically goes through and featureizes all of this data. As you may know, with like image classification, for example, you're given an input as an image, and your goal is to go through and first featureize it, split it up into some important features that help you determine its class, and then you actually go through and determine the class. So the first step is to take your data set and featureize it like this. And then afterwards, you can use these features when you have various different tasks. When you're learning the features also, you're usually trying to learn features that help you with all the tasks that you see during your training time. And then let's say during the testing time, I give you a new task n+1, for example, and I give you another small data set to work with it for that. You would start off with the features that you learn in the meta learner during the training time for all of these n tasks, and then adapt that to your new task that you see. So again, the general goal is to reuse knowledge from the previous experiences whenever faced with a new task. And the way that this happens is you learn a wide variety of tasks which use similar methods. So you don't really learn like tasks that are very different and have absolutely nothing in common, because there's not much to take from one task to another. So usually like a common example would be recognize a bunch of different images and then given a new image that whose class is not in the original training set, be able to classify that this belongs to a new image, to the new class, sorry. Okay, so the first example of meta learning that we'll go through is one-shot learning. And the task here is that given a new image which belongs to a set of classes, you're recognizing the new image which belongs to a set of classes where each of the classes only has one example. So concretely, you can think about this as, let's say in like a company, you have a face recognition system. On the first day, you take a photo of the employees, and then from there on, you want to be able to recognize them based on only that one photo. Previously, you would have trained your system on as many different faces as you can find, but ultimately, you don't train them on the specific one employee that you get during the testing time. So that's kind of the idea of one-shot learning. And usually this is very useful when retraining is expensive, and either because compute power is expensive or because you can't really find more examples of training data and you only have one example. So our goal is to generalize well to unfamiliar instances that are of a similar nature but are actually unfamiliar still. So an example of this is again by OpenAI. What they have here is that they have these three images over here, and when a user draws in a new image, it says which of these three images are most close to the new image there. And you only get one example of the new image. So in their training time, they would have seen multiple different hand-drawn images, but they probably wouldn't have seen these specific ones. And then whenever a new image is drawn, it says which of the three has the highest probability of being the new image over there. Yeah. Okay, so the key points to take away from this is that the training data set can have many examples of many different classes. And actually, the more classes or the more different types of examples you have, the better, because you're trying to show the model as many different tasks as possible. But the classes in your test set must not also be in your training set, because if they were, then the model could just go back to the training data and have more than one example of each image. So let's say I asked you how you would do this one-shot learning task without using neural networks at all, using as standard ML techniques as you possibly can. Does anyone have any ideas? And a hint is this picture.
I mean, it reminds me a little bit of nearest neighbor. But
yeah. Do you want to expand on like how that may be related to one-shot learning?
Well, you can have an example that you've never seen before. You can just look at what examples it's near to and take like a majority vote of those, and that would be like in the family of nearest neighbor techniques.
Yeah, that's exactly kind of the motivation behind this. So if you didn't use neural networks at all, you could use a straight one nearest neighbors approach. And with here, you're basically using some sort of a distance metric for each new point. So you're seeing, based on my distance metric, how would I find out which of the classes that are available is this new point closest to? Right? But then with nearest neighbors techniques, you usually have to define what that distance metric is. And that may not always be suitable depending on what your inputs are. For example, if your inputs are images, which are usually in very high dimensions, many of the standard distance metrics don't really scale well to such high dimensions and don't perform as you expect. So the model that we'll be going over to kind of tackle this one-shot learning problem is the Siamese network. And here you're basically using a neural net to as a distance function. So instead of us defining that we'll use like the L2 distance or the L1 distance, we'll let our neural net figure out what the appropriate distance function is given the specific inputs. So here specifically, if our inputs are two images over here, we want to do some sort of like pairwise distance between them. Like one standard thing to do if you weren't using a neural net is just to maybe like subtract all the pixels in here and minus these ones, and then just like sum all that together to get one single value. But if you did that, then that's not very invariant to the various transformations that an image could take on. For example, if you like rotated the image or you shifted it over, then just directly subtracting the pixels wouldn't really be as effective. So instead of us defining the distance function, we'll pass these two images through a neural network. And then at the end, that'll return a series of a vector of features that correspond to each of the input images. And then based on these vector of features, we'll take a sort of distance between them then, like an absolute difference or something, and then sum through those to get kind of the final distance between the two images. So we're looking at the distance in the feature space, not in the original space. Okay. So as you may have noticed from before, let's say actually we looked at these two images and we just sent them through two different neural networks and they have the exact same structure. Do any of you see like a problem that this might have? Like, why would it not be such a good idea to take two images, send it through two neural networks which have the exact same structure, like the same number of layers and everything, and then once they're represented as features, just do a subtraction of the features and like come up with something, a distance like that? Yeah.
It might end up the same.
Yeah, that's like kind of on the right track. Did you have something?
Well, for one thing, bless you. For one thing, the result wouldn't be commutative.
Mm-hmm. Yeah, that's exactly right. So basically, if you had two of the same images, especially because your neural nets are started off with like random initializations and then they'll be updated in their own ways, there's no guarantee that if you input two of the same images to both of them, your features will be the same for both of them, right? And that's something you want because the reason we're going through and like featureizing this is to get some useful information, but that has to be consistent with each other. You can't have like two different ways of featureizing because then it's not consistent to take like a direct difference between them. So instead what we'll do is we'll run two images through the same network. So it's still shown as different networks over here, but you can think of it as the values of the weights in each of the layers are exactly the same for both of them. So practically you could just run the same image through the same network twice and then get two different features here and then go from there. Yeah. And with most neural networks that you may have seen before, usually you take like an image and you're trying to predict the class of it directly. So the features are computed with which features will help me best label this image. Right? Here instead what we'll do is that we specify that our interest for these features is that we want to maximize the difference for maximize the difference of features for images which are in different classes. So we don't care as much whether this network can accurately classify each of the input images. We care that if the two input images are different, the features have to be really different. And if they're both the same, the features have to be really similar. Right, so that kind of allows this network to take on the property of being a distance function rather than a normal classification network. Does that make sense? So the way that we do this is when we go to the loss function, you'll see that that's how we basically are able to specify how to make sure that these features maximize the difference if they're different classes. Okay, so just to be concrete about this, the input for the network will be a pair of images, x1 and x2, and the output would be the difference between x1 and x2 once they're in the feature space instead of in the original pixel space. Okay, so the loss function that we have will be the one that basically says how do you update the weights in the network so that it like performs the way that we expect it to. So the inputs to the loss function will be the distance between x1 and x2, which we'll call d, and we'll say y is the label, and y will equal 1 if the label of x1 is not equal to the label of x2. And if they're both the same label, it'll be 0, and I'll explain exactly why that is later. So before we go over what this loss function means, our goal, let's say DC over here is the difference between two images in their feature space if they're both the same class. And DW is if they're both different classes. We ideally want that the difference between images in the same class are closer than images of different classes, right? So DC will be equal to D or less than or equal to DW, right? But if we have just that simple inequality, DC is less than or equal to DW, then when you set them both equal to 0, the inequality is trivially satisfied because always 0 is less than or equal to 0, right? And we don't want the network to just set them both set whatever the input is, set the output to equal 0, so this inequality is always satisfied. Instead, we'll have a margin term alpha. So this is the margin term, and this is basically saying how much lower does DC need to be than DW for us to be satisfied, kind of. And the larger you set this margin term, the further apart you're trying to push apart the distance for images that are of different classes. Does that make sense? Okay. So looking at this now, just if we brought dw over to the other side, then you would have alpha minus dw. But when we look at the loss function, how does this fit into the loss function? Let's say first that both of the images have the same class. In that case, y is equal to 0, right? So when y is equal to 0, this whole term will cancel out because it's 0 times something, so that all goes away. And 1 minus 0 is 1, so the loss will be equal to d when y is equal to 0. So when they're both the same class, the loss is equal to d. And d is the distance between both of the images, right? So when we're trying to minimize the loss, we're just trying to directly minimize the distance between both of the images if they're both the same. If y is equal to 1, that means both of the images have different classes, right? So in that case, this term goes to 0, and we're only left with this term over here. And when we look at what the loss function is, it's essentially equal to alpha minus d. We have this max over here also, but the reason we have max is because we're taking the maximum of this value and 0. So let's say the distance is greater than or equal to alpha. So the difference, so when it's greater than or equal to alpha, that means it not only satisfied what we want, but it went above what we wanted, right? We wanted it to be at least alpha apart, but it went beyond that, right? So in that case, we can just set it equal to 0 because it already satisfied the constraint. But otherwise, we're basically trying to minimize alpha minus d. And especially because it's the minus d term over here, you can think of it as kind of maximizing the difference when they're both different classes. Does that make sense? Okay. So we have this loss function here, and one more thing is when we're looking at what we wanted initially, we had, and if we pulled the dw over to the other side, it would be dc plus alpha minus dw. And this kind of looks similar, like you have the d term here and then the plus alpha minus d term over there. But the reason why we have the y and 1 minus y is because we don't know which of the terms, if the d is when they're both the same class or different classes. So we're only given one pair of images and they can either be same or different. So always one of these, either DC or DW, won't exist. So that's why we have the 1 minus y and y to kind of filter for that. Okay. So now we'll go on to actually how to implement this, and we'll do that using the Omniglot dataset. So basically what this dataset is it's kind of considered the transpose of MNIST. So MNIST is like a classic dataset that's used in many machine learning techniques, and it's handwritten digits. And basically you have 10 different digits, and each of them have many examples. With Omniglot instead, you have many more examples of digits or of characters in general in all sorts of languages, but you have way fewer examples for each one. So this is kind of naturally lending itself to like the one-shot learning techniques. So the goal basically is to say, given 2 images from this, train on as many of the training images you want. But in the test set, when you're given new characters, given 2 characters that may or may not be of the same class, the goal of the network is to say, is this the same class for both of them, or are they both of different classes? So that's what we'll be doing in the demo. If you haven't already, please go to this link over here and download the notebook from there. And also this demo will be using PyTorch, so if you don't have that already, try to install that. It works with the pip install, so you can try that. Great. Okay, does everyone have the link? Yeah? Does anyone need this still? Okay. So if you haven't already, just try to run the import cells, and if whatever libraries you don't have, try to go ahead and install those. Okay, and I'll get started with like going over some of the introductory parts of this notebook. So first we just have a few helper functions to like plot an image and show an image and stuff like that. We have like the training directories and batch sizes and basic things. And then the first part is basically we have to create some sort of a custom dataset class that goes through and picks out two images, and we'll be able to use those to say whether the images are same or different. So instead of just taking the entire all of the images at one go, we're going to go through and pick two of them at a time, and then we can use like an iterator to like loop through and get batches of whatever size we want. So this is all filled in for you guys, but just at a high level, what's going on here is that you get the folder of the images, and then basically first you pick one image 0 as like a randomly from the entire set, and we want approximately 50% of the images that we're training on to be of the same class as the pairs to be of the same class, and 50% to be of different classes. So we go through, and if they're the same class, we pick within that class, and otherwise we just pick throughout the entire data set. And then we just do some pre-processing to resize it and make sure it's in the format that's required. And basically what this is returning is we're returning image 0 and image 1. And then we'll also return the label, which is equal to 0 if they're both of the same class and 1 if they're of different classes. So image 1 tuple is the label of them, so you're checking if they're different and returning 1 if they're different and 0 if they're the same. So just then if you go through and you want to, or actually I'll start running these. Okay, so if you visualize these, you can see each time you run it, you get different images. Here. And when they're both different, it returns 1, and when they're the same, it'll return 0. But the first part of like the notebook that you guys will be working on is defining the Siamese network. So we saw from before that the network looks something like this, right? Where you have a series of convolutional layers, then some normal fully connected layers, and then taking the two inputs, you're going to compute some sort of distance. So that'll be the first part that you fill in. So for the convolutional part, I wrote out over here what the structure of the layers should be. So basically, first you have a padding layer so that the size always stays the same throughout the convolutions. Then you have a conv layer followed by ReLU, and then a batch norm layer. And then you keep doing this like 2 more times. So, and then here's like some hints on how you can use like the convolution functions in PyTorch. But the first step is basically the first set of layers are given over here. So go through and using this architecture over here, fill out the next 2 sets of layers. And that'll basically take care of finishing up all the convolutional layers of the Siamese network. So feel free to like work with the people around you. Like take 5 minutes to do that, and then I'll go over like how to do it. Okay, how's it going? Are people making progress on this? Does anyone need more time? Um, should I go over it then?
Sure.
Yeah? Okay. Okay, so the first layer, the ones that were already given, I'll just go over that so the rest of them make a bit more sense. The input is given as a grayscale image, right? So there's no color. So that means, and we reshaped it earlier so that the width and height would be 100 by 100. So it's a 100 by 100 grayscale image. So that means that the image as an input only has one channel. And if it was like a standard color image, it would have 3 channels. So first, we just use reflection pad 2D just to make sure that the size stays the same as we use the rest of the layers. And then first we're saying that we want a conv layer that has 4 3 by 3 kernels. So and the way that the con2d function works is that it takes the first input is the number of input channels. The second value is the number of filters, which is also equal to the number of output channels. And then the third one is just the kernel size. So we have that over here. One input channel, 4 output channels, and a kernel size of 3. And there's 4 filters, that's why 4 output channels. And then there's ReLU that we're using as a nonlinearity. And then batch norm, we're using 4. Batch norm takes in the number of features as the input, so you can think of that as the number of channels coming into it. And here, because we have 4 channels going out, that's why batch norm takes in 4. But for the next part, we start again by doing padding. So it's the same function as before. And then the next one, it's asking for 8 3x3 kernels. So does anyone know what to pass in here? So we're using the same function as before, con2d. But does anyone know what the arguments should be to this? If we're doing 8 3x3 convolutions, or 3x3 filters, yeah. So the first input would be the number of input channels, right? So based on what this outputs, what are the number of input channels at this point? 4? Yeah. Does everyone see why it's 4? Yeah. Because here you're using 4 different 3x3 kernels, and each kernel will create its own activation, and there's 4 different activations. So now it's there's 4 channels going out as an output. So the first value is 4. We want 8 3x3 convolutions. So what should the second value be? 8, yeah. And then our kernel size is 3. Yeah. Okay, so then we're just doing ReLU again. And then when we do batch norm, what should the input for this be? And this takes in the number of channels basically that the convolution layer outputs.
8, right?
Yeah, 8. Yeah. Okay, does anyone have any questions on this? Yeah. So basically, it's a way to normalize the activations after each, wherever you put it basically. And you can think of it as kind of, let's say each mini batch is like feeding in something that, like a distribution that's slightly different from each other. You don't want the weights to change too much based on each one that has a slightly different distribution. So this normalizes it. Yeah. Okay, so for the next one, we have the same thing as before, only we have 8, yeah, we still have 8 3x3 kernels. So mostly the same as before. So we start again with doing padding. Then we have this one, the conv layer. But here, what should the first, it's still 3x3 kernels, but what should the input number of channels and output filters be? So the input channels should be,
8.
Yeah, 8, because the last one outputted 8 channels. And then how many filters are we using? Yeah, it was 8 again. So yeah, that's how we do this one. And then apply ReLU again. And then batch norm, the output of this is 8 again, right? So that's why we just do batch norm of 8 once more. Does everyone understand this? Any questions? No? All good? Okay.
Don't forget to delete the last comma.
Oh, right. Thank you. Okay. So the next part is, okay, so right now we finished basically this part over here where we have all the convolutional layers. So the next part is the fully connected layers before we like actually do the pairwise difference. So the fully connected layers are given over here. And first, ignore how we get from the convolutional layers to the fully connected layers right now. But the input they're just basically a series of linear layers and ReLUs stacked on top of each other. So we're taking an input that's initially 8 times 100 times 100 and eventually transforming it into something that's 5-dimensional. And then we'll do the pairwise distance on the 5-dimensional vector. Okay. So now think about how we're going to run this actually. So let's say we're given one image. So don't think of the pair of images right now. Just say we're given one image. How do we run it through this network? And you may not know the exact syntax on how to do it in PyTorch, so that doesn't matter too much. Just think about what the steps should be and talk about that with your neighbors, and I'll just go over it in like a minute or so. Do people know what's going on? Okay, okay, we'll just go over it then. Okay, so we have something here that has all of the CNN layers together and then all the fully connected layers together. So the first step, once you're given an image, what should we first run on it? Based on this picture over here. What would be the first thing we do once we're given an input image?
Convolutional layers?
Yeah. And the reason is because we don't have to do any flattening or anything of this because the convolutional layers take in the image as a 2D image instead of flattening it out first. So we just do that, and the syntax for doing this is we say self.cnn1, and then we pass in the input x. Yeah. Okay. So now we finished running all of the convolutional layers on it. And the next step would be to do the fully connected layers, right? But is there something that we have to do before we start doing the fully connected layers?
Maybe need to reshape.
Yeah, and why would we need to reshape?
Like maybe it's too high dimension. Is it like four axes or something?
Yeah. Yeah, and the fully connected layers only, for each batch, or for each example, it only wants one vector of like 1D instead of a multi-dimensional one. So the way we reshape in PyTorch is we can say output.view, and then we pass in whatever shape we want here. So the shape of output right now is batch size. The first dimension is the batch size, so like how many ever examples are going through the network at once. And then the rest of the dimensions are whatever the network outputs. So it's like the image in whatever dimension the network has it right now. So basically, we want to keep the batch size. We don't want to mix up images of different examples, basically. But we want whatever high-dimensional image we have right now to be fully flattened out into a single vector. So the way we do that is we say the first view takes in the shape, what we want to reshape it into. So the first thing we'll do is we'll say output of size, the 0th dimension of that. So that's the batch size. So we're saying the first dimension is still the batch size. And then the second dimension, we're flattening it out completely. So we'll just say it's -1. And this basically means infer what the rest of the dimension should be to match the number of values in the input and output. So whatever we passed in here, so the output value, so like of the CNN that comes out, whatever the rest of the dimensions are, basically multiply them together so that everything is preserved. That's what the -1 means. Okay? So now that we have this, the next step is to run the fully connected layers, right? So we'll do that by saying self.fc1 of output. And this is already flattened out, so this should work. Okay, any questions? So now we basically came up with this vector for one image so far. We said we would ignore this for now. So now the final step is to kind of put it all together. Given a function that basically takes an image over here and runs it through this entire network to get a vector out like this, how do we basically do this pairwise distance function? So we said before that our network would be taking in a pair of images, x1 and x2, and it's returning a distance, right? And so far we have a function that does this portion of it. So now how will we use that function to kind of finish up this network and like do what we're supposed to do? That's like the next step to just think about for a minute or so. Okay, does anyone need more time? Should we go over it? Yeah. Okay, so we're given in, this is basically the forward pass of the network. That's what this function is. So we're given in two input images, input 1 and input 2. So what's the first thing we should do? So like when you're given this image over here, what would the first thing do? What should you first do? And you already have a function that takes an image and takes it out to a vector like this. Yeah. Yeah. So the first thing is basically to like use this network to featureize the first input image. So the way we do that is we'll say output 1 is equal to self.forward once of input 1. So that basically takes this image here and gets out that vector there. Right? So now we have one image featureized. So the next step would be to do the same for the other image also, right? And because we said before that we want the weights of this network to be exactly the same. So what we could have done is we could have gone through and defined another network and like specified that all of the weights have to be exactly the same as this first one and like don't do anything different. But an easier way to do it is just to run the second image through the same network again also. So you don't have to like worry about all that extra overhead. So the next thing we'll do is we'll say output 2 is equal to self.forward once of input 2. Does that make sense? Okay, so now we have output 1 and output 2, which are both feature vectors of the input images. Right, so what should we do now that we have these and we want to return a distance? Yeah. Yeah. So we'll use that to compute the pairwise distance. And so the function that we'll use PyTorch is built-in distance function. So we'll say pairwise distance of output 1 and output 2. And this basically, so output 1 and output 2 right now are 5-dimensional vectors, with a vector with 5 dimensions. And this pairwise distance function basically returns a single scalar that's like the Euclidean distance of those two vectors. And actually, because we're passing in batches of images here instead of just a single pair of images, it'll do batch size by 1. So like a vector containing all of the distances for each pair of images. Okay, any questions about like any of these forward pass methods? Okay. So the next step is we finished doing this. We're able to get some sort of a distance metric. The next step is to do the loss function, right? So the loss function, it's over here. And basically, it'll take in the pairwise distance between two images, and that's what d is. So you can think of d as a scalar, and another scalar, which is y, which is the label representing whether the images are same or different. So now I'll give you a few minutes. Go through, or actually first, so here's the loss function class that we'll use. And here we have this alpha term over here, right? So the margin will say that that's self.margin. And then the distance and label are given over there. Go ahead and implement this loss function over here. And so the functions that you'll probably need to use are listed over here. Mostly you'll need to use the power method and like the clamp method to do this max of a value and 0 there. So take a few minutes to like try to implement that. Okay. Should I go over how to do this? Does anyone want more time? Yeah. Okay. So So the first step we have here, we're first doing 1 minus y. So I'll do that like that. And then multiplying it by the square of d. So we have the Euclidean distance in here. And this is, we want the square of that though. So we'll say torch dot pow, input is Euclidean distance. And then we're squaring it. Yeah.
Isn't y called label within the scope?
Oh yeah. Mm-hmm.
I think you can also just use the double star instead of the torch dot pow.
Yeah, I think maybe you can, but the only concern is like the distance would be not a scalar but like a vector, so I don't know if it handles.
No, it's like the same function. It just calls it the pow.
Oh really? Okay.
The overload.
Sure. Okay. And then the second one is now we're doing this part over here. So we'll say label times, for the max function over here, we're taking the max of some value and 0. So that basically means this value, whatever it is, cut it off if it ever goes below 0. So we'll say torch.clamp of self.margin, which is alpha, minus Euclidean distance. And then we'll say that min of this is equal to 0. Okay, so whenever this value goes below 0, cut it off at 0. And then we're just taking the power, squaring this again. Okay. Any questions about this so far? Yeah.
I guess I'm kind of confused. Can label only ever be 0 or 1?
Right now it is. It has to because this is the label that's passed in by this data function over here. So basically it's passing out whether they're both the same or different. So it's always 0 or 1. Okay. So one thing to note is that our label is coming in, it's 0 or 1, but it's a vector of 0 or 1s because we have like a batch size going in. And similarly, our distance is a vector also. So we want to our loss function should be minimizing a single number though. It's not minimizing a vector. So we can convert this into a single number by just taking the mean of it. So we're taking the mean over the batch. Like that. Okay. Any questions about this? No? Okay. So we'll just run that, and then so that's basically it. We defined the network, we defined the loss function. So the rest of like the training code is basically given, but I'll just go over it. First, you're just loading in your data set, setting your optimizer and stuff like that. And basically in this loop over here, for your number of epochs, you're going through the data set, all of it each time. And you have image 0 and image 1 and their label of whether they're equal or not. You passed into your network both image 0 and image 1, and you get a distance out of it. And then you're saying your loss is equal to this function on the distance and the label. And then you're just trying to minimize the loss, basically. Okay, so you can just try to run this right now. It'll take a while to actually finish running, so around like 10 minutes or so, but you can just make sure that the loss is mostly decreasing. Sometimes it'll go up every few iterations, but overall, like in the long term, it should be decreasing. So I'll just show you what the results should look like. And we'll be posting the solutions afterwards also on the same GitHub link. So after you train it, it starts off around 2-ish, I think. Or here it starts off much higher. But after you finish training, basically the training curve should go down mostly, even though it goes up occasionally. And then we can evaluate to see how does this actually do on our task. So our task was to take in 2 images and say if they're similar or different, or if they're the same image class or different. So we have, I'll just stop this one. So we have a way to base, so we created another data loader which returns out the two images and their class labels. So we go through and for each of these images, x0 and x1, pass it through the network and get the distance out. And we'll call that the dissimilarity. So the distance, if it's higher, that means they're of different classes, and if it's lower, that means they're of the same class. So when you just like look at these for different images, like if they're different images, the dissimilarity is pretty high. If they're the same, usually it's lower, but sometimes it's high also. And if they're exactly the same, the good thing is it's 0, so that means everything went through properly. And you can just look through this, but a few things to note here is that, first of all, we didn't use a very deep network. We used a relatively shallow one. And also, just to make this, like, the training not take forever, we're only using a few classes in the dataset. We're not using the entire dataset. So if you did that, then the accuracy would go up much higher because you would have a lot more training data and such. But here also another thing to note is that our network is taking in 2 images at a time. So remember in that video I showed you where you had 3 different drawings that a person drew, and then the 4th one, it would check which of the 3 it is. That one, it was comparing against all 3 of it. So it could say this one has like 90% chance, this has 5 and 5, or something like that. Here you're just looking at 2 images, and the reason is because we don't know how many images or how many classes, potential classes, there'll be in our test set. So there could be 5, there could be 10. So the network really can't be predefined in a very standard way to say, let's show the probability over the distribution over 10 different values. So we're just doing a one-to-one comparison instead. So the way we can like kind of generally see how well does this do, after we know what our test set is, we'll know ahead of time how many points will be of the same class as this one that we're referencing, and how many will be different. So we can just sort this by their dissimilarity, and the lowest, how many ever are supposed to be in the same class, we can just assign the predicted value to be of that class. And then the rest of them, the predicted value will be not of that class. So doing that, now we have class labels for all of these images, and then we can go through and compute the accuracy as normal. And this approximately performs like 85% accurate, which isn't bad. I've seen papers where they show around 90%, so this is pretty good. But this is like a really active field of research still, and like potentially there'll be much better ways to do this, where you can take into account what the other potential classes will be also and stuff like that. So yeah. But just like a few remarks, yeah, so we need much more training data and probably a deeper network to get much more higher accuracy and learn more, and this is still an active area of research.
Okay, so that was all about one-shot learning. Now I want to talk about a couple other areas of meta-learning. And first I'll start with an area that a lot of people don't typically think of when they think of meta-learning, but in some sense it's really the same problem as a lot of these other typical meta-learning tasks people talk about as meta-learning. So what I'm going to talk about first is transfer learning, which is the idea of trying to learn things. They're trying to transfer knowledge from one domain to the other in the context of deep learning. So here's a sort of example, is that you have some canonical data set, huge data set on some task. For example, in this image, it's ImageNet. We have a huge amount of images and labels for them as to what they are, like dogs, planes, cats, fire trucks, etc. And then we have a huge amount of labeled data, and we can train models that do really well on this fairly complicated task on this huge amount of data. So there are ImageNet models that get 90+% accuracy on certain tasks. So we have a really good model for this image classification task. But then say we have a new task that is, maybe it's still image classification, but our class labels are outside of ImageNet. That would be one of the easier tasks to transfer to. Or you could have a completely different task where you're looking at images and, say, trying to segment them into what's in the image. Like, for example, draw a map over the pixels, and the same colored pixels are the same object. So You see this a lot in sort of self-driving car research, is where they're trying to segment the image and like draw bounding boxes around what's a car, what's a pedestrian, what's a road, etc. So your sort of your target domain could be all sorts of things, but you can still use the knowledge the model learned on this huge data set to do better at learning in your target domain where you might not have nearly as much data. So to try to train a model from scratch in that domain might be absurd and like impossible. Um, and the the thing about image data in particular that suits it well for transfer learning is there's a lot of information about images that is common to pretty much any task you want to do with images. So like edge detectors and things like this that we know pretty well convolutional neural networks learn at some point in their layers are common between any kind of image task you want to do. You're always going to be looking at where the edges are to be able to understand that image. So this is why transfer learning is particularly effective for images, because there's so much common information between different image tasks. And in terms of how we practically do transfer learning, typically we take our source model that's trained on a huge amount of data. Say here we have a VGG 16, maybe VGG 19, one of the two models, where someone's trained a very large convolutional model on ImageNet, and it does very well on ImageNet and on that particular task. And then we want to take their pre-trained weights and use them as a good sort of initialization point or a good feature extractor for our new task. So those are the sort of two things I just mentioned, the two techniques, fine-tuning versus retraining bottom layers. So fine-tuning, actually let's start with retraining layers. So the ideas I was talking about before about why it's effective for images is that we learn these things that are common to images, and those things are typically learned in the convolutional layers. So the motivation is, hey, why don't we just leave all the convolutional layers as they were in our pre-trained model for ImageNet, and then just get rid of the dense layers at the end that are actually like predicting classes. So this works really well if you have another image classification task. Like you have some class that's not in ImageNet and you want to learn to identify that class, you can take a pre-trained ImageNet model, get rid of the layers on the fully connected layers on the end, and then retrain those fully connected layers for your particular task. And then you're not limited to have the same number of output classes as are in ImageNet and those sort of things. Another thing we can do is what's called fine-tuning, where we take this pre-trained model, freeze some of the earlier convolutional layers, because earlier convolutional layers in convolutional neural networks tend to learn sort of more simplistic features, and therefore they're more likely to be common between different tasks. And then we fine-tune later convolutional layers, which means we use the weights that the pre-trained model has as an initialization point for our model. And from there, we retrain, typically with a lower learning rate than the original model was trained. But yeah, we retrain those convolutional layers. And this is typically used for more complicated image tasks. And when we're transferring to other image tasks that are more complicated than just classification or have a lot of different classes that are very different from the ImageNet classes, these sort of ideas, that's when we want to actually be able to alter some of the convolutional features, not just the fully connected layers on the end. And then we can add our own fully connected layers as before. So these are sort of two ways that you typically see transfer learning done. And then I'll just briefly mention why I think this is sort of still similar to the ideas of meta-learning. And it's really about how you're taking knowledge in one domain and sort of canonical knowledge about a domain and applying it to a whole bunch of different tasks. So here the canonical knowledge is, okay, what are images, what are edges in images, so on and so forth. And then we might have a specific image classification task, like, okay, what is a dog, what is a cat? And that's what we're trying to specifically learn, but there'll be a whole bunch of different tasks, so we want to learn a sort of meta learner that does all right and does all right at like the sort of base knowledge that it needs, and then from there it can quickly learn new things. So that's how transfer learning sort of fits into meta learning. And it turns out transfer learning is used in a whole lot of places in industry. If you see any industry applications where they're using image classification and the classes aren't in ImageNet, most likely they took some pre-trained model from ImageNet and retrained it on the classes they care about, unless they're Google and they have a billion gigabytes of data that they can just throw a new model at. So any smaller sized companies using transfer learning for those sort of tasks. And this was a slide from Andrew Ng's presentation at NIPS 2 years ago, predicting the sort of importance of different subfields of machine learning in industry in the future. And he views it as sort of an exponential growth of the importance of transfer learning and not so much growth in other areas. Now I wanted to talk about some of the newer, I guess, flashier meta-learning methods that are based on sort of gradient methods, and they typically do tasks called few-shot learning, where the domain is you're given a bunch of tasks, and you have a bunch of data that is different from the tasks. And then you can use that data to train some sort of meta-learner, and then you only get a few examples from each task in order to learn how to do those tasks. So I'll show a couple examples later, but the basic idea for these gradient methods for meta-learning is instead of learning a model, instead of learning some sort of map from X features to some label, we learn the optimizer for models. So we learn a way to create a model from features X, and some way to create a map from features X to a label Y. I think that's the sort of basic idea behind these models, these methods. And the first method I want to talk about is model agnostic meta learning, and I'll try to go over this diagram here because it can be a bit confusing at first sight. But model agnostic meta learning is a sort of more recent method, came out of a lab at Berkeley. The idea here is that in this picture we have 3 different tasks that we're trying to have some sort of meta learner be able to learn quickly. So the idea is that this solid black line is the path of our meta learner's parameters in parameter space. And then these different parameters here, labeled with the subscript 1, 2, 3, are the parameters that it gets to after doing a few gradient updates for each specific task. So this is where the meta learner gets to through its training of the meta learner. And then once it's here, it says, okay, this is a decent point where from here, in only a few examples, I can then go and learn these different places in parameter space that are good for these particular tasks. So this is sort of the good point that does all right for multiple tasks, but from here it's very easy to quickly learn how to do other tasks. And so the meta learner's goal is to get to a point like this where it's easy to learn its particular tasks. And how it does this in model agnostic meta learning is following sort of the gradient of its parameters summed over a bunch of different tasks. So it takes samples from its set of tasks, and then from those tasks, it will sample examples in those tasks and try and use its parameters to try to solve those examples. And then using the loss it gets from the tasks that on those examples, it will use that to update its overall parameter. And then when we go to new tasks or new unseen data in tasks that we haven't seen before, it will just see a few examples, but hopefully it'll be in a good enough spot already where it can learn from those few examples what is a decent thing to do in that new task. So I have a couple examples of MAML working here. So you can see at the top it says 0 gradient steps, 1 gradient step. I don't know if it'll show 2 here. Yeah, just 0 and 1. So you can think about, You can think about zero gradient steps as being this point. This is where the meta learner gets to that it thinks is a good, decent sort of initialization point that can do well, quickly learn to do a bunch of different tasks. So the zero gradient step here is, if it goes back to it, you can see it's just sort of walking around. The goal for this environment here is to get this spider creature to walk around, and the learner has no information about the dynamics of the spider creature or anything like that. It just has to learn from a reward. It's a reinforcement learning problem. So then you take this spider creature and it's sort of learned to walk around sort of aimlessly at zero gradient steps. And then you can think of the two different tasks that it wants to learn as here as a goal velocity of 0, so standing still, and a goal velocity, I think I covered that, but it's a goal velocity of 3, so moving quickly. And you can see that the original zero gradient step wasn't doing really either of those tasks, but then with only one gradient step on each of these tasks, you can see it does a pretty good job of doing what that task asks. On the left, it's standing pretty still, and on the right, it's moving pretty quickly. So this is the idea of a mammal, is that you can get to this state where with only, in this case, one gradient step, you've done really well on two different tasks. And on the left side, you can see another example of this with a different environment, this sort of like stick creature. I don't know what that is, but it's trying to walk. And on the left, it's trying to move backwards as the task. On the right, it's trying to move forwards. And you can see the sort of zero gradient step is just sort of doing neither and just like keeping its balance. So it's learned to keep its balance, and then with one gradient step, it can learn to go forwards or backwards. So that's the idea behind mammal. Do people have questions about this?
Is one step generating faster than, or in terms of training, than, let's say, usual policy gradient?
Right, so the typical model for a policy gradient, typical regime that it would follow is, okay, I have a given task, I'm going to follow my policy gradient to get the best policy for that particular task. And then if I want to do a new task, I have to retrain the whole thing. And that takes time. And so the idea here is, I train one model that is like, has some fundamental information about my environment, and then from that one thing, I can do just one gradient step or a few gradient steps, and from there, I'm really good at that particular task that I took those one or two or three gradient steps in. So instead of having to train a new model for each task, you now have one model that you only have to train for like one step to do well at different tasks.
So that one step is faster.
Yeah, well, like a typical policy gradient method would probably take on the order of millions or even billions of gradient steps. Any other questions? So there's another very similar method. You might get confused between this and the previous one because they look almost the same. It's a very similar idea, but this is called meta SGD. And it's basically the same idea as mammal, but they have this added alpha parameter. And so this diagram is actually a bit better to see the idea of mammal as well. You can see it's labeled meta learning and learning adaptation. So it's getting to this point by meta learning, and then it does this sort of short few gradient step adaptation to the various tasks. And this is an illustration of how it's learning. And along the way, it's saying, okay, for each of these tasks at my particular parameters for my meta learner right now, this is the sort of losses and the gradient of the losses for each of my tasks that I would get with those parameters. So I'm going to update using that information. And the addition of this alpha, what it does is it's sort of like the idea behind it is sort of like a learning rate. It's learning not just the parameters, but also this learning rate. So if you have a typical optimizer, an optimizer also is given a learning rate. So the idea behind meta SGD is to sort of learn this optimizer where you're learning the learning rate. And this learning rate is actually a vector, so it's not just a learning rate, but it's like a sort of a learning rate for each value in our vector loss here, or vector gradient here. And so there's not a huge difference between this and mammal other than this alpha parameter. So there, yeah, it's really pretty much the same idea. The only other difference is they do this sort of a little bit of different training regime. So before, when I was talking about mammal, what we were doing is if this box said mammal, it was like, okay, we're feeding our current parameters in here, we're training for a bit on our new tasks, and then using the loss on those tasks to update our meta learner parameters. And then the only change with the meta SGD is we have this alpha, and then instead of just taking the losses we had on the training data in this task, we train on this task, get some new parameter theta prime I for each task, and then using those parameters fixed, we run the model corresponding to these parameters on some test data in that task. And then we use the losses on that test data to update our meta learner. So it's a slight difference there, but again, a very similar idea. And you can see it's illustrated between each of these steps, it's updating its internal meta learner parameters. So, any questions up to this point? Yeah. Yeah, sure. So the alpha is essentially involved in how we're updating our parameters. So you can see it down here when we're creating this this equation here, theta I star equals theta minus alpha, and then this circle dot just means like element-wise multiplication. So this is a vector, and this is a vector of the gradients of the loss with respect to theta. And then we element-wise multiply these, and then that's how we update our parameters in here. So we have this meta learner parameter, and we do some training on the tasks, and that gives us these losses right here, Li, sort of visualized as gradients here. And then using those losses and our alpha, we have this element-wise multiply between alpha and those losses to create this new theta I prime. And then we train on some we test this theta I prime on test data from those tasks, and then using the loss of the test data, we take the gradient of this loss here with respect to theta and alpha to update our new theta and alpha. So to answer your question, the alpha is involved in this step here, how we get from the training on this theta and updates to that theta to this new theta I prime here. So you could think of it as a learning rate in the sense that if you forget everything below this box and just look at the thing in the dotted box, you could think about this as a typical supervised learning task, where you're saying, okay, I'm going to do a training step. That somehow updates my parameters, and then I have some learning rate that I multiply that update by to get my new parameters. So I have some gradient update on my parameters, and I want to multiply by this learning rate so that it controls like how fast I'm updating. The only difference here is it's like a vector learning rate where you're controlling not only how fast it's updating, but how fast it's updating different parts of your parameters. And the meta learner is actually learning this parameter. Any other questions? Okay, yeah, just briefly, meta SGD and mammal are very similar. The slight differences I mentioned are how they do these updates on test data in meta SGD, as well as this extra parameter in meta SGD that we just talked about, this alpha sort of vector learning rate idea. in terms of when you would use meta-SGD versus MAML, as I showed, MAML has had some really good success in these reinforcement learning environments. I haven't seen many papers, or I haven't personally seen any papers on meta-SGD doing these reinforcement learning sort of tasks, but I have seen comparisons of meta-SGD and MAML on tasks like OmniGlot, which Nikita was talking about. And on these sort of tasks, I've seen papers that show the meta-SGD does better, but again, these are sort of empirical results. So I think because they're very similar, I wouldn't say there should be any preference to either. Yeah, and so that's sort of the two main gradient-based meta-learning ideas. There's a third one called Reptile, which is almost identical to MAML. I think it was made by the same people as MAML, and it's just essentially a simpler version of MAML that uses less memory and less computation. And so they do that by getting rid of some of the passing around of gradients and things like that by doing a more simplistic thing. As is often the case with machine learning and deep learning, the most complicated ideas come out first, and then people will figure out ways to simplify them. So the last thing I wanted to briefly talk about is zero-shot learning, which is a really active area of research and a really hard problem. And the problem here is we're given some image to classify, but we've never seen this image or anything in the class of this image before in our training set, ever. So it would be like if we trained a model to classify cats and dogs, and then we gave it a bird and asked it to tell us what a bird is, what the label for that bird is. So it's a very difficult task in this sense, and there's a lot of active research in this area. And so the general idea behind solutions to this problem, I don't really, I'm not going to go into solutions because it's such an active area of research, it becomes sort of like a reading group of papers at that point. But the basic idea behind most of these solutions is we take an image and then we embed it into some sort of knowledge representation of that image. So here it's saying, okay, this thing is black, it's also white, it's not red, it has stripes, maybe it'll say there's green or something like that. You know, there's lots of this sort of embedding of the attributes of this image. And some methods do simple things like just having like a table of attributes and saying, just like binary, does it have this, and they have some fixed number of attributes, and they can do all right on these sort of tasks. And then based on this knowledge representation, this embedding, we can take it and compare it to a knowledge base. We have some sort of knowledge base of sort of like, okay, what do zebras have? What sort of attributes do zebras have? This is represented in our knowledge base. And typically this is also embedded in some way, probably similar to the knowledge representation of our image. But based on this, the knowledge representation of our image and our knowledge base, we essentially do sort of search through our knowledge base for what matches our image embedding the most. So in this case, we're saying, okay, these attributes match a zebra, so we'll call it a zebra. But you can sort of say that, like, in some sense, this is a zero-shot learning, might be not quite so zero-shot because we have this idea of what a zebra is represented in our knowledge base. But in terms of like the actual image task, we've never seen anything that looks like a zebra before. And yet these methods are still finding a way to sort of classify these kinds of images. I think there are a couple other methods, but almost all of the ones I've seen use this idea of embedding and embedding it into a space where we can then search through a sort of knowledge base in this embedding space and compare in that sense. Yeah, so some concluding thoughts on the whole sort of area of meta learning that we've talked about so far. I guess just to sort of briefly conclude is it's really new field where research is very active, and it's definitely still in the research stage where people are finding new things very often and nothing is fully developed yet. And because of that, I'd say it's a really great area to sort of get involved in research in and that sort of thing. Yeah, so any questions at this point? That's all we have. Oh, and please fill out the feedback form if you can. Yeah.
I think one of the so basically the first model we talked about is just a new loss function.
The Siamese networks.
So
Yeah, it's this idea of putting two identical networks together and then having this smart contrastive loss function to essentially create a distance metric is what we're doing.
so can you put any or the model can be very different. For example, you can use like VGG and
Right. Yeah, you could use whatever you want here as long as they're identical and they share their weights. That's the key thing, is that basically you have the same embedding of this image into this vector, no matter which network it goes into, so you get commutativity. Any other questions?